If you walk down the aisle of any modern data center, the physical scale of the infrastructure is immediate. You are looking at millions of dollars of computing power, stacked floor to ceiling. But beneath the flashing lights is the physical layer, Layer 1. These are the thousands of miles of cabling that provide the electrical and optical paths required for every server, switch, and router to communicate. You can update a software stack with a few keystrokes, but if you realize your physical cables can't handle your data load, you face days of manually ripping out and replacing massive bundles of wire. This creates a constant tension for IT teams. Vendors push fiber optics as the standard for every environment, yet traditional copper still dominates local edge deployments. Treating your cabling strategy as an afterthought is a costly mistake. If you get the physical layer wrong, you instantly throttle the most expensive hardware in your rack. Let's look at how the two primary mediums actually compare. This split-screen matrix pits thick, twisted pair copper against a single, hair-thin fiber optic strand. When we populate the first two rows for maximum throughput and distance, fiber outpaces copper. It pushes more data across the kilometer-scale stretches of a campus. But when we add the third metric, base hardware cost, the advantage flips. Off-the-shelf copper cables and their native switch ports are significantly cheaper. Finally, looking at the environmental footprint within the rack, that single fiber strand takes up a fraction of the physical volume of a heavy copper bundle. If you base your decision entirely on raw speed tests, fiber wins every time. But that ignores the realities of data center budgets and localized deployments. You are balancing localized durability and immediate cost against high-density reach. To see why copper holds ground, we must look at the top-of-rack deployment model. Here, a server needs to send data to a switch sitting just a few inches away. For these short intra-rack hops, direct attach copper, or DAC cables, are highly effective. They are thick and rigid, meaning you physically wrestle them into place to hear that solid click into the server port. That bolt comes with a high degree of durability. Copper requires no optical conversions and plugs natively into existing legacy hardware. But density is copper's enemy. When you stack dozens of these thick bundles together, they create a solid wall that traps heat, blocking server exhaust fans and forcing your cooling systems to work overtime. You sacrifice long-term scaling for localized cost efficiency. This is why copper remains dominant at the edge. Cabling economics change when your network must bridge multiple buildings across a massive corporate campus. Instead of heavy electrical impulses, your data travels as rapidly pulsing light, shooting instantly through a microscopic, transparent glass filament. Because it uses light, fiber is immune to the electromagnetic interference that plagues long copper runs, maintaining bandwidth over several kilometers. But that light has to be translated. You need specialized optical transceivers plugged into the switch at both ends to convert the light pulses back into electrical data the servers can process. Those transceivers drive up your upfront capital expenditure. You're spending significantly more just to light up a fiber connection. Fiber enables much larger network architectures, but it shifts the primary financial burden from the cable itself directly onto the endpoints. To see how density forces your hand, look at this 2D map of a spine leaf network topology. It is the current standard for enterprises managing massive internal data flows. The rule of spine leaf is that every leaf switch must physically connect to every spine switch at the top. This supports east-west traffic. Modern servers spend most of their time talking laterally to each other, rather than reaching the external internet. In older designs, you would face oversubscription, a traffic jam where too many servers try to push data through too few uplink cables at the same time. By wiring this dense interwoven mesh, SpineLeaf ensures there are always multiple high-speed paths available, eliminating those oversubscription bottlenecks. If you tried to build this mesh with heavy, twisted pair copper, you would run out of physical space in the cable trays and create a thermal barrier that blocks airflow. When you upgrade to a high-density core topology, the spatial and throughput requirements mandate a move to fiber optics. Moving past the theory, let's look at this effort versus impact quadrant chart to understand the daily operational reality. We plot fiber optics in the top right quadrant for high impact but high effort because glass is fragile compared to rugged copper wire. Managing high-density fiber requires strict adherence to properly routed patch panels and meticulous labeling standards. A messy rack or poorly labeled strand leads to accidental breakage during routine maintenance. Deploying fiber demands a level of operational discipline and maturity that smaller, resource-strapped IT teams may not have. To decide where to invest your physical layer budget, we use this decision flowchart, starting with a simple question. Are your cable runs exceeding 10 meters? If the answer is no, follow this path down to deploy copper and DACs. If you manage isolated racks or legacy edge sites, stick to cost-effective direct-attach copper. You preserve budget without over-engineering your environment. If your runs exceed 10 meters or you deploy a spine leaf topology, follow the path straight to fiber optics. For network architects building high-density, multi-building campuses, the upfront cost of optical transceivers is the mandatory price of admission. Your network's maximum speed is dictated by its weakest physical link. Match your cables directly to your topology and leave the marketing hype at the door.